some use cases of these things. So basically, what have we done over 2 lectures? We talked about my notion of the infeasibility of truth, right? Instead, what we do is we try and search for understanding, but we'll always remain infinitely removed from that. That motivates that everything has to be parameterized with uncertainty. So we talked about how we can parameterize this ignorance or beliefs about things, and we talked about how we can then do statistical inference to update our knowledge from experiments. So we can mix our incomplete knowledge with incomplete data to hopefully get something. We talked yesterday, I gave you this quite simple notion. Really, it is really simple. As I said, there's like 3 lines of code to do this. As a very nice interpretable object that we can encode beliefs about functions. And then we did, at the end of last lecture, we did the real grunt work, right? But even though this is a lot of grunt work, it's just math, right? Here is where the clever science comes in, right? This is just what we're left to just do the hard work. So what would we use these things for? What would we use these types of probabilistic models for? And I'm going to give an example in work that I spend a lot of time doing. So I like working with scientists, like proper, physicists, chemists, and all these people. And what very often they have is they got some really cool simulators for things, right? Physicists have ODEs for absolutely everything, or SDEs, all sort of things. These things are often insanely computationally expensive. Think about weather forecasting models, for example, right? It's like, you need to be pretty much bigger than a country to be able to compute these things that comes out. The United Nations does them, right? Okay? And then I got the real world, right? So very often, what I end up doing is building what I call statistical emulators, which are things which are inspired by how we think the world works, but I don't try and be correct to the world. I just try and fit the statistics of what these models do. And then this will allow people who work in this world to be able to explore what things they should actually run, right? Where should they spend their time doing the really expensive computations? So I throw my cheap statistical model on this. They're expensive, but relatively to running a climate simulation, they're dirt cheap, right? And then, of course, I also have real-world data. It would be silly not to use the real-world data in this as well, to try and fit my, try and figure out parameters that these should have and so forth. And very often we got multiple types of simulators. They could be of different fidelity, for example, right? So very often we build simulators or emulators that take multiple simulators into account, some real-world data. And this is really where a probabilistic model should sit, right? I think. So then, what is the big thing that I tried to show with that graph? Well, it's not a static scenario, it's an active scenario. So I'm just going to show this, how we think about this, right? So here's me, or an agent of sorts. Now, the agent sees the world, or some simulator, or something. I tried to do some form of experiment at this, something happens, I get some data back, I analyze this, and then I design a new experiment. Everything we talked about so far has been static. Machine learning shouldn't be static. The world's not static. Here's not a data set. We work on it for 10 years. Result, right? No, the world's happened during these 10 years, and we should take that into account. So this really fits well, right, in the notion of thinking about us as using machine learning for doing science, right? So we have an hypothesis, and then we do this loop more than once, right? Everything I said was just one loop so far, right? That's clearly not how the world works. So today, we're going to exemplify this through a very, very simple problem. We are going to have a function, and I'm going to try and find the minima of that function. This could, for example, be if you have this, it could be, I have this ODE that I want to solve, and I want to find out what parameters I should use for this, right? That could be something like this. So we're going to talk about black box optimization. So I have some function of that's explicitly unknown to me. I don't know the functional form of this, but I can query the function, right? And we want to find the minimum of this. We're going to use this through building surrogate models or emulators. This is where we're going to take all the stuff that we talked about so far. And then we're going to do sequential decision making in these models. We are going to take the data acquisition process as a modeling itself, right? So I have a finite set of data to begin with, and then I go out and ask the function, what is your value at this specific point? And then towards the end, we're going to do something a bit crazy. We are going to think, well, computation is a very interesting thing that we do a lot of. How about if we add uncertainty to the notion of computation itself? And we see computation as a data acquisition process. Now we can do something really funky. So the thing I'm going to talk about is Bayesian optimization. That's usually what it's referred to. So the setting is this. I've got a function over some bounded domain X, and my task is to find the minimum of this. The function is explicitly unknown. I don't know what it is, right? You can think of, for example, I'm a doctor and I'm interviewing a patient. I don't know what's going on, but I can query information, right? The evaluations of F may be noisy, right? So I can't necessarily completely trust them. The one thing I know for sure is evaluations is expensive. So I want to find the minima by querying this function as few times as possible. So we can take an example of this, would be an election poll, right? So there is some underlying function where you take all an enormous amount of inputs and you get the election result out, right? It's called running an election, right? Now, I don't want to run an election to do a poll of an election, right? So that means I need to query people in a clever way, right? That's the task that we are going to try to think of. So, worst thing you can do is to get ourselves, what we need to beat will be a completely random search. So say that I'm happy if I find something up to epsilon as an error, right? And let's say I assume something about my function, otherwise we can't get any bound. So I assume some Lipschitz continuity, so basically saying how quickly the function roughly moves. Now, this would, if I have a d-dimensional x, this would require c over 2 epsilon to the power d evaluations. You can do the math for some problem that you're interested in, and you're going to see that's a lot. So, what we're going to do to address this is we are going to build a surrogate model of this function. We're going to try and constrain this by inputting beliefs over our functions. So, we talked about this already, right? We have a notion of building prior distributions over functions. So now we're going to use them, right? The nice thing now, it comes back to exactly your comments the other day, is that GPs are really nice because we can make our beliefs super, super strong, but we don't exclude anything, right? So they're a really natural way of doing this. Great. So let's just do this. We're going to work with this function the whole time. It's a ridiculous function. It's very simple, right? It has a local minima and a global minima, right? So the first thing I'm going to do, I'm just going to say, I've seen these 2 points. I have made some assumptions about smoothness. So I've formulated my covariance function. I just put a GP on this, right? And what I'm going to do is that I'm now going to take this distribution. I can evaluate that everywhere. And I'm going to take the minima of the mean the whole time. And I'm going to put that in. And then I'm going to update my model, going to take the minima again. Okay, let's see what that does. So, that was the minima, so I inputted that, I go a new model, now that's the minima, that was definitely not the minima, dunk, 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 I keep doing this, and now you see what happens. It's homed in on this thing, it has very, very low uncertainty on this, and if I keep running this, it's basically going to be stuck at this point, right? So, what was the thing, there's a big thing that we've talked about that we didn't use, right? We didn't use the uncertainty. So, when we're confused and trying to solve problems, you know my solution to this, we go and think about beer, okay? So, person walks into a bar, right? So now it's the first time you're in a bar, so you like sugar because you're genetically, you know, done to like sugar. We all like sugar. So you look for the thing that you know, and you have a Coke, right? Sorry to tell you, you're going to miss out on stuff, right? Because if you never explore a bit more, you're going to miss lovely English beer that looks like this. Now, you have to balance this thing, though, because if you explore too much and go and try things, this is the weirdest alcohol I've found. Smoked salmon-flavored vodka. No one should have to drink this, right? So there's two things that we somehow need to balance, right? I need to balance exploitation, which means this is good, I'm going to keep drinking this, with exploration, so that you move from that to this, right? So these are the two components that we need to balance. For those of you who are students, you're excellent at this, right? How do we do when we study for an exam, right? 2 months before an exam, I do all sorts of weird random questions. I think maybe there'll be a question on this, and I try myself, like I aim to fail to learn. Then you go into the exam room, what do? You just exploit everything you know, right? Cool, so it also has a temporal aspect of this, right? Cool. So, that means, what should we use to balance exploration with exploitation? Well, that's uncertainty, right? Uncertainty tells me, here, I'm really uncertain. I think, if you put a gun to my head, I think the value is here, but I'm not very certain of it. It could also be down here, right? So now we're going to exploit that. And just to show the model that we currently have, how uncertainty gets reflected, I'm going to do this plot where at each point, each slide, I'm going to take this posterior distribution, draw a sample. This is the first sample, and then I'm going to plot the minima of this, right? Cool? This parameterizes my knowledge, and now we're going to see how the knowledge of the function reflects on the knowledge of the minima, okay? So, let's draw another sample, let's draw another sample, let's draw another sample, dunk, dunk, dunk. Let's see how many I had. I had this many. Cool? Now we can see these follow a very nice and clear distribution, right? They're clearly concentrated around here, right? So now, what I would really want to do in order to do this search, I would want to parameterize this distribution, right? The probability of the minima of the function. Sadly, that's something I can't formulate, right? If I could, this histogram that I would get here, if I had that in closed form, that's exactly what I would want to do the whole time, right? Take the maximum probability of the minima at each step. Can't do that, so we need to do something slightly different. What we're going to do is that we're going to formulate something which we're going to call an acquisition function. So it's the function that tells me how I should acquire data, right? And we're going to say that the next data point that you're going to query, the next x location, is the x point that maximizes this acquisition function. This acquisition function is a function over x, so the whole domain. It takes the data that I've previously seen, and it takes whatever model I have at the current step n, right? Now we can formulate, by doing iterative maximizations of this, a sequential decision problem, right? This will be good if maximizing this function is easier than minimizing the other function. If this would be more expensive, I've just shot myself in the foot, right? But if we can formulate a cheap function, that. And what we want to do is to design this function so that it balances exploration and exploitation, right? Okay. So the easiest thing, now you can see a reference from 1933. This is called Thomson sampling. This is basically what I showed you before. What we're going to do is that at each iteration we're going to draw one sample, commit to that sample, take that minima and put that back in. It's the simplest thing you can do. Often it's very, very useful to do Thompson sampling. If you do sequential decision making, this should always be a baseline, and you'll be surprised how hard it is to beat often. Okay? So let's do this. We're going to see multiple plots of this. So I draw a sample. I take this minima in, draw another sample, put this minima in, draw another sample. It's very close to the previous one. And I keep doing this, and eventually I found this thing, right? Tricky thing with Thompson sampling is that it can go very wrong because you might draw some weird sample in the beginning, and that sample is going to have a huge effect. So it's also very important, if you run Thompson sampling, is to run it over multiple random seeds initially. So you get a diversity, and then you look at the distribution over the minima towards the end. And you want to minimize that variance. Okay, cool? So I just wanted to show you that because it's the simplest thing to do. It kind of makes sense. It directly reflects my knowledge that I have from my surrogate model. You can come up with, and the literature is full of an enormous amount of different heuristics to define these acquisition functions. What we're going to do is try and define the acquisition functions a little bit more principally. So what we're going to say is that we're going to define what we call a utility function. Okay? So we're going to say, define a utility function which characterizes how much is the utility of seeing a specific point. Okay? And then we're going to say that the acquisition function is the expected utility. So we're going to take my belief currently about the function, and we're going to take the expectation over this utility. Okay? And that is going to be our acquisition function. So utility of each value, given that we know the function, and then I integrate out my belief over the function at that point. Okay? So the most useful one that we this is really where most Bayesian optimization uses, is a utility function called expected improvement. So this here is currently my best estimate. So this is the lowest, if we're minimizing, this is the lowest value that I've currently seen. I'm going to say that observing anything that's worse than the lowest value has zero utility. And everything I expect to be better has a utility that's scaled by how much better I think it is. Okay? This might not be right? We all know this if we go back to any training that we do with people. Sometimes doing worse is actually a very good step to doing better. And everything I do here is greedy, right? Right? We can clearly think, and I think this is super interesting work that people should be doing, looking at doing this non-greedily and actually taking into account that doing something bad can actually lead you of a better strategy to doing better. So it's all very simple at the moment. If I compute this acquisition function, it's super easy to do. Lots of math, but it's really interpretable actually. So what would I have? I would have, let's look at this one here. I am integrating the function values from -infinity up to the current value I have, right? That's how I get the utility. Everything above that is zero, no utility, of the difference between these. That's going to lead me to a very, very simple structure of a function. Here, I got the mean minus the current best value. The current best value I have minus the mean times, and this here is the error function or the cumulative Gaussian, right? So it's just looking at the cumulative Gaussian up to where I currently am. We'll show you graphically. So this here is basically exploitation. It takes the mean, so this is exploitation. Exploration gets encoded by this term. So if I have Here is the variance at a specific location. If this is high, that's exploration, right? So exploitation, exploration, and it factors that out really nicely. I don't think I'm beeping. So the way it looks, you can see it very clearly. This here is the acquisition function. It effectively is this. This is the current minima. I just cut it through here, right? And then I flip it around. That's how expected improvement looks like, okay? Now we can see what this thing does. You are gonna pick something out there. You're picking something in the middle. Dunk, dunk, dunk. I think that plot is slightly wrong. That shouldn't be that way. That's effectively how an iteration of this goes. And now, this is a little bit better of balancing exploration and exploitation in this case. So that's expected improvement. Now, that's basically Bayesian optimization. That's it, right? All the stuff that we learned about Gaussian processes and all this stuff, or whatever model you have of uncertainty, this is what you can do as soon as you got a decision process, right? If we got a belief over something, we can make really informed decisions, right? So, think about what we are required to do. First, we encode all the knowledge that we have about the function in a GP prior, right? This is the thing we talked about yesterday. It requires you to go out to the person who've generated the data, sit and talk, buy them lots of coffees, and then come up with, the function is smooth to this scale, it has discontinuities, it's this and this and that, and blah, blah, blah. You try then, you go away, you sit on your room, you do the math, you try and formulate a covariance function that encodes these beliefs, great, right? Then you randomly sample some data, right? Often, this is the case where people have given you some data. Now you have to be careful about this, right? Because people who evaluate data, they don't do it randomly. Think about a doctor, right? They don't try random medicines on people just for fun, right? So the data you're going to get is definitely not going to be random. It's going to be very biased, and that bias is often a good thing, right? Because they know what they're doing, right? You just want to nudge them and help them a bit, but it's very important to take into account it is biased, right? Okay? Then you specify your acquisition function, if I could spell that word. This, you think about how you would do this thing. This is a really useful thing to have a human in the loop as well, right? If you can generate data and say, oh, now I think this, what do you think of this? And the doctor said, no, that makes no sense. People don't weigh 300 kilos, right? So we don't need to go out and test that, right? Okay, great, right? So here, it's often good to have your function, but also have a human in the loop. And then you evaluate, you maximize your acquisition. That means you get new data, you get this new data, and you re-estimate hyperparameters or all the things you have. You do your whole machine learning loop here, and then you loop this thing until your bodice is gone. The analogy with writing an exam is when you have to hand in the paper, right? Okay? No more work can be done, right? And this thing here is, hopefully, you found this reasonably obvious, right? It was not, if I go uncertainties, it's not rocket science. This thing here, I think, is one of the really few machine learning things that are really making a difference at the moment. There's companies, industries that are massively investing in this and doing lots of work. If you know, for example, AlphaGo, initially in the paper, they didn't say, but there came a follow-up paper. This was the key thing of getting things to work. And it was really simple, exactly the thing that I explained to you, an expected improvement and a Gaussian process, with in that case a Matern 5.2 kernel, was the thing that made them able to get AlphaGo working, right? And I have worked with several companies doing, for example, optimization of wind farms, optimization of electrical engines. This technique is super, super, super useful. If you're training a large neural network, why don't you run a BO loop to set your hyperparameters? It's kind of standard practice nearly now, right? So this is it of that. Cool. Do we have any, how are we on time? I'm trying to figure out. 20, so I got 40 minutes to go. Fantastic, we're going to be on time. Great, and then we can have lots of discussions afterwards, potentially as well. So now, do we have any thoughts or questions on this? It's kind of obvious, right? It's not, no, but it's not rocket science to do this, right? It's very natural. What do I do when, think about, we are incredibly good as human beings in sequential decision making, right? We explore uncertainty. That's what we do, right? We're really excellent at this. And this just means if I'm going to model which has nice uncertainties to it, we should use that in this framework. And also, every problem that you work on are any interesting problems. Data is not static. Data comes continuously. Should you just say, oh, forget, run it again, forget, run it again? Obviously, you should have a part in saying, oh, if you give me that data, I really think we can do better, right? Data acquisition is super expensive, nearly always, right? I've seen lots of talks on health here, right? That's the key example. Always expensive, yeah? Or in the renewable energies, you can't say to someone that has a wind farm, oh, can we just randomly set all the parameters, right? No, you can't. You have to be very careful about the parameters that you choose. Great. So I'm going to now take this to the extreme in some ways, and I'm going to talk about something which I think is probably the most exciting thing that's happening in probabilistic machine learning at the moment. So what do we do with uncertainty? What we do with uncertainty is that we make further decisions to reduce our uncertainty. We want to get our head out of the sand, right? So we spend all this work, lots of approximations, all this stuff to get these uncertainties. So how can we use them in a clever way? We saw BO, great. It feels like quite a natural example of this. Now we're going to take this a step further. So think about this. So I didn't show this plot before. This is just the Gaussian process fitted to this thing. We initially started with this function, and then we said we have some noise on it, right? And then we have a function. Actually, one thing, I've just shown these blue plots the whole time, but that uncertainty actually factorizes in two terms. It factorizes into the noise I have, the red thing, the irreducible uncertainty, and then it factorizes into my uncertainty or my lack of knowledge of the function, which is the green thing at the moment. A Gaussian process, these two just separates, very simply, okay? But then half the talk yesterday was about showing lots of math. There were lots of approximations and assumptions. We did this sufficient statistics assumptions and all this stuff, which I have no idea if they're true, right? So how do I know that that's actually the noise and this is this? Maybe it's just that I did a really bad computation, and actually if I could do this in closed form, this would be completely different, right? Always when we do computation, we have these nice continuous models, right? Can a computer even represent a continuous number? No, it can't, right? So all my computations are also approximations. So this is not a new idea. Poincaré wrote this. We're going to read this because it's quite nice. The need for probability only arises out of uncertainty. It has no place if we were certain that we knew all aspects of the problem. But our lack of knowledge also must not be complete. Otherwise, we would have nothing to evaluate, right? If you truly are in a state, I have no idea, probabilities are completely unnecessary as well. There is thus a spectrum of degree of uncertainty. While the probability of the 6th decimal digit of a number in a table of logarithms is equal to 6, being equal to 6 is 1/10 a priori, in reality, all aspects of the corresponding problem are well determined. And if we wanted to make the effort, we could find out its exact value, okay? This is true, right? If I got a table, a logarithm table, there's truth there, right? Right? I could do more and more computations, and eventually, possibly, I'll get to the truth. The same holds for interpolation for the integration method of Coutts and Gauss, right? Poincaré, 1896. So, the idea then is to say, when we do uncertainty quantification, we normally just have two terms: aleatoric uncertainty, which is a randomness inherent in our system, or noise in our measurement. These are the things, it doesn't matter how much I measure, it's not going to get removed. The only thing I can hope to do is determine the level of the noise. And then we have epistemic uncertainty, uncertainty related to our ignorance of the underlying system. This is the thing that I'm aiming to reduce. And my decisions should clearly be different based on which uncertainty I'm reducing. The argument now is that we should add a third one: computational uncertainty. Uncertainty related to finite computation or intractable computations, right? And now I should make different decisions if I really want to have factorized all these three parts. Okay, so everything that we did, we talked a little bit about uncertainty here, we spent a lot of time talking about uncertainty here, that led us to nice uncertainties here, but we forgot this bit. Now I want to do this propagation of uncertainty through all these things, right? That's the aim. So, what would having this uncertainty allow me to do? Well, computation is really, really expensive. So, what I would want to know is that if I run this computation for an hour more, what will I possibly gain, right? Maybe all the uncertainty that's left is actually noise, and now you're just wasting your MCMC running more time, and the only thing, you're not going to get any better, right? Your work is better going off doing something else, maybe acquiring data, right? What should I do what should I compute in order to reduce my uncertainty as much as possible? Clearly, you have a spectrum of things that you want to do, right? So say that if I'm estimating the minimum of a function, where should I spend computational power? And then, if you're given a computation by someone, well, it's very rarely the end result. You're going to put that into a next system, so you would really want to be able to quantify how much can I trust the thing that comes out of there. It's like my students, right? They know anything I've derived, they shouldn't trust, right? They re-derive it to make sure, point out my errors, right? That's how they've learned how to quantify uncertainty in me. So, therefore, how precise should we do downstream tasks, right? And there's a beautiful saying by von Neumann, so 1947. Round-off errors are strictly very complicated, but uniquely defined numeric number theoretical functions of inputs. Yet, ignorance of their true nature is such that we best treat them as random variables, right? Rounding in a computer, you can see this, right? This is one of the things I question a lot, right? So I run some code, I'm just thinking, I'm just ramping, longest double floats everywhere, and it would just be good, right? But I don't know, my computation have truncated this, so in the end, I might have 8-bit precision, right? One, I would really want to know that. Number two, if I knew, that's where all it went gone, I can just do 8-bit calculations for a long time here, and my code will be tons faster, take much less memory, and everyone will be happy, right? So, this here, I think, is really key. So, we're going to then go back to something that we now know what we can believe in, and we're going to do some stuff on that, right? We know now, hopefully, that we can make beliefs about functions. And then we're going to try and think about computations on functions. So, we got this function. Again, what we're going to think about, let's try and formalize this problem. I have some form of latent quantity. In this case, say that it's a distribution over functions, or it is a function, but say that it's a distribution for now. And then there's some quantity that I want to compute from this. This is a function. Let's make that the minima, or the integral, or something like this, right? Now, there's an operator, f, that goes from the latent quantity to the quantity of interest. So in this case, if I knew the function, this is the process of integration, okay? Now, I'm a machine learner, so what I try to do, I don't have access to this, I have access to sample data, I try and design an algorithm that takes me to the quantity of interest, right? Great. If we think about what most machine learning is effectively trying to do this. I got a distribution of some latent stuff that I don't know. I clearly know what I want to do with this distribution, right? Compute something. But what I often do is that I get some sample data, I design an algorithm that tries to approximate this, and then I apply the same operation. That feels like a really, really or silly thing to do, right? Say that that's the minima. I only care about the minima. I don't care about modeling the function. You're wasting an enormous amount of effort modeling something that you don't care about, right? Can we do better by including the quantity of interest? And then, because we're talking about active learning in this setting, we are going to say that the data is not static. So I have another operator, the data acquisition operator, which queries this variable and generates the data set such that I can build an algorithm to get this quantity of interest. Now we can think about most tasks that we do is to make this series of operations commute with this, right? We want going this path, which is our path, be the same as this path, right? If we look at Bayesian optimization in this sketch, it's effectively this, right? So I have an unknown function. I don't know what it is. I can query it. If I knew what it is, it's just minimizing the function, I will get the optimal value. Now instead, what I'm going to try and do is that we designed acquisition functions that took my belief over the function. That gave us data. From that data, we updated our model to give us this, and then we minimized this. Now, the thing here is that this is kind of the bad way I said before. We're still modeling the function, but by picking data that was relevant for finding the minima, this is not a good model of the function. It's a good model of the part of the function that's relative to the minima, right? Okay. So, what can we do with this, right? So let's give a couple of examples that people are working on. We can look at problems of linear algebra. All the stuff I talked about in the plenary talk is actually solved by linear solvers with matrices which are 20 million squared. I'm not going to solve inverses of that in my computer. I'm not even going to store them. So we solve approximations of that. We quantify, you can think about optimization, we've already talked, analysis, or the thing that we're going to talk about now, which is a really good example of this, is quadratures. We're going to talk about how we can integrate a function. So, let's talk about integration. It's just the quantity that can be computed from a function. So, another statement, integration is a significant numerical problem in many fields of science and engineering. It's a key step in inference where it's encountered when averaging over the many states of the world consistent with observed data. Indeed, a provocative Bayesian view is that integration is the single challenge separating us from systems that fully automate statistics. More speculatively still, such systems may even exhibit artificial intelligence. So, if we could crack integration, it will be a very, very good thing, right? And we won't. Right, so we're going to look at having a function which we're going to integrate over some measure. Now, if you want to go back to why it's really important in Bayesian statistics, that measure is used, our transformed measure over the parameter space, and F could be a conditional distribution, right? But really, we're just going to think about it as this now, right? Okay? So, now, what's the easiest thing I can do? First thing we learned when we did integrations, right? We said, well, what I'm going to do, I have this function, I can evaluate it, I'm going to do a grid of some sort, and then I'm going to do some rule like this, right? I'm going to take these bars, and I'm going to calculate their area, and I'm going to sum them up, right? We all did this. Great. So that's one algorithm, right? So now, where does uncertainty come into this? Well, this grid is going to give me one value. This grid is going to give me another value, right? There's a design choice that I make that induces different values of the integral. So the design of the algorithm induces some form of distribution over the quantity of interest. So let's change this and think about the algorithm itself, the computation, as statistical inference. So the definition, according to me, of a numerical method is that it's something that estimates a function's latent property, integral, given the result of computation. Now, numerical algorithms therefore takes data in the form of evaluation of computation and aims to return the prediction of the quantity of interest. What is statistical inference? Statistical inference takes data in the form of measurements of observed variables and aims to return predictions of the quantity of interest. They're exactly the same, right? Numerical analysis, a computation, is exactly the same as if I go out and query some data, I measure something in the soil. How is that different from putting in a number and getting a number out of a computation? Exactly the same thing. So let's think about computation as inference. So now, if I could do this, let's see this, we've all done this, and I'm going to skip that to be quick. So we're going to now take the quadrature rules that we saw before, and we're going to treat them as statistical inference, and we'll see what will happen. Please stop me if there's anything that's unclear. Right? So what I'm going to do, as an example, I'm going to take a computation that I can't do. I have a function, e minus sine 3x squared minus x squared. This function here is super easy to evaluate the integrand. The integral doesn't exist in closed form. So here I have a problem where I know this thing, it's super easy, but I don't know the quantity of interest. It's intractable. So now, either I can just say, okay, screw this, I'm just going to do lin space and hope for the best. But I know loads of things about that. Why should I throw that information away, right? That's how it looks like. Now, what we're going to try and do is we're going to try, the ideal thing to be able to make clever decisions is to observe this function and derive a posterior distribution over its integral. If I can do that, I could do active learning, because I could try and find the wise that minimizes the variance of this. I can balance exploration and exploitation, all sorts of things. So let's just do something funny to show you why this works. I got the function, I got a GP prior, I've sampled the hell out of this thing, and here's the histogram of the integrals of all those blue functions. Now let's see some data. The histogram changes, see some more data, more data, more data, more data, right? Now, the value of the integral is nearly determined, right? So, can we do this in a bit more clever way? Well, first thing, we know a lot about this integral. It's strictly positive, it's bounded above by this, therefore I can even bound the integral to be the square root of pi. It's very simple. Let's see if I got a plot on this. No, I didn't have a plot of this. But it's quite easy to see that it's bounded by this, and therefore I can bound it from above. Now, it's the same thing as we went with before. I have all this knowledge. Should I just throw it away when I apply my algorithm? It feels stupid to do that, right? That's going to mean I'm going to require a lot of data. I have some stuff that I know, so if I increase that, I'm going to need less data, right? So same thing as before, right? How can we implement our knowledge about this? So let's write this up as a Bayesian inference problem. We're going to encode our knowledge about the function f. We're going to F here, we are going to say that F connects to my observations, so potentially I have noise in my observations. And then I'm going to say, how does F connect to the quantity of interest, which is in this case the integral? Okay? Now, I'm going to do this very, very simply. So we're going to put a Gaussian process prior here. We're going to say that I have absolutely no noise at all. So I've got a delta function that sits on each point. So each function, I'm only looking at a function that goes straight through the data. No problem not doing this. It's just that we will see a bit cleaner math of me doing this. And then I'm going to say, if I know the function, well, I can compute the integral. It's just a linear operation if this is a Gaussian process, or it's just a linear operation. So I know exactly what F is, right? So now, if I combine these two, if I put a Gaussian process, this is a linear operation. So Gaussians are closed under linear operations, which means the joint distribution of y and f is just a Gaussian. It's a Gaussian which has the normal mean, which is what we defined, or in terms of the posterior, if I've seen some data, it has a covariance function. The covariance of the integral is just going to be the double integral of the covariance function. And the cross terms is going to be the single integral of these. So now I got a joint distribution of this and this, that's Gaussian. That means I can condition this on that, right? It's just a multivariate Gaussian, right? That's it. And we know how to do the math of this. So I can just do that conditioning very simply. So if I do this, you'll see something like this. So here is the prior, very, very wide. Then the measure that I'm going to integrate over this is also going to be a Gaussian. It's just to make this a bit cleaner. Here is the Gaussian over the integral. So I see one point, dunk, 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 right? So now, in this case, I just picked points. But now I have exactly the same object I had as in the Bayesian optimization setting, and I can just apply an acquisition function to this, and I can do much, much more clever integration. So, another cool thing you can do, if I got this Gaussian, in this case we condition this on that. How about doing something completely different? Let's condition the function values on the integral, right? Here, I have seen these data points, and I have said, give me only samples such that every function integrates to 4. I can change that and say, give me just functions that integrates to 1. This is a really cool thing, right? Think about other things where you can define a distribution which constrains the integral, right? I've never seen this used, which I think is funny, because I bet you there must be cases where you really want to constrain your integral. Someone would now say, cool, I should model probability distribution or densities with this. It's really hard to constrain the model to only be positive with the Gaussian process. Otherwise, that would be like home free. Cool? Okay, so you can now do, when people do quadratures, they do acquisition functions, or the information operator, that thing that queried data, either by exactly what we said, try and minimize, reduce the variance of the integrand, or you can try and reduce the variance of the integral itself, which is this thing. People do this, it works really well. It's actually a super powerful method, and a lot of times, I think if you got reasonably low dimensional problems, instead of doing MCMC or variational Bayes or something, try this. There's really good packages out for this as well. So now I'm going to come to the last thing. I'm going to try and be quick on this. Why I'm really excited about this. So let's do something weird. Let's pick a covariance function which is basically Brownian motion. So I'm specifying a GP that has this covariance function. So it's piecewise linear functions, okay? Covariance looks like that, okay? Now, what I'm gonna do is that I put this prior in and do exactly the quadrature rule I had before, and then I compute, take the mean of this, right? So I take the expected integral. What do you have there? Does anyone recognize the mean? Exactly. This here is the basic quadrature rule that we all, it's the trapezoid rule, right? Now, why am I so excited about this? Well, it's the normal trapezoid rule. The algorithm that I've now designed that comes out from this, I designed it by saying, I think the data looks like this. Therefore, the algorithm just pops out. This algorithm is tied to what I thought the data was, right? This is a super, super powerful statement. Now, I can do inference in this where to sample, for example, right? You see how cool this is? I'm saying, I think my problem looks like this. What's the optimal algorithm to solve it with? And this is not, you know, it's not super surprising. If you got a function which is piecewise linear, the trapezoid rule, you know, it's there, right? You can do this with more advanced things as well, and there's a whole community trying to rederive classical numerical algorithms based on this, right? So, I like to define then the trapezoid rule as this. The trapezoid rule is the posterior mean estimate for the integral f under a centered Wiener process prior with covariance like this. This tells me this is the definition, right? It's now just not taken out of thin air, right? And this I think is super cool. So, you're not impressed. Some people are impressed. I saw nodding heads of like, this is cool. Okay, I'm gonna try and convince you again why this is not just cool, it's very important. So, this thing here, we all agree, if you don't have your hypothesis, can't really determine your results. Where have statisticians gone wrong before? Right, least squares, which I defined before. You know, there's a battle. Was Lagrange or Gauss the one who came up with this? Lagrange had some algorithm that reduced error. The assumptions that was said here was not clear at all. Gauss made a very clear statistical model that said, if your error is independent and Gaussian, it leads to this. Therefore, I can interpret Gauss' result. If the planet wouldn't have appeared in the sky, where Gauss said, we would have known Giuseppe's errors were not Gaussian and not independent, right? This allows us to do no science whatsoever. This does. Second thing, factor analysis. Spearman, 1904, he proposed some weird thing, an algorithm that extracts factors from data. Not saying anything what they actually were, right? For those of you who know, this led to horrible things. This was one of the things that eugenicists did to prove that certain people are more intelligent than others, right? Horrible stuff. Factor analysis, read this paper. It talks about general intelligence, right? In ways that are horrific, right? Now, Hotelling in 1936 defined a clear statistical model of factor analysis that allows us to say, and if you look at that model, I can clearly say, oh, like same result, but I can clearly say, oh, your assumptions are bullshit. That's not how the world works, right? So, therefore, I think it's really important that we do this thing with computation as well. So, you can look at this. This is minimize in NumPy. There's a method flag, you can choose all these. Which one should I choose, right? I run them all and they give different results. Clearly, I should be able to say, I think my function looks like this. That means I should use TNC, whatever that now is, right? We clearly need to quantify these things. So, there's tons of numerical algorithms for every problem under the sun. They work really well. Like, it's amazing. Look at the amount of old Fortran code that basically all of our work relies on, right? ODE solvers, all this stuff. Code from the 80s, 60s even. They give different results on the same problem. What's the prior they implement? That's what we really need to understand. So, final quote of the day. Oliver Busquets gave this talk. He said, Oliver Busquets has described the deep learning community as a gigantic genetic algorithm. Researchers in the community are exploring the space of all variants of algorithms and architectures in a semi-random way. Things that consistently work in large experiments are kept, the ones that are not working are discarded. The community is evolving on one set of parameters, keeping most of the time the optimizer fixed. And therefore, his argument was that what we've actually done, neural network has evolved to make Adam the best optimizer. If we had a different optimizer, maybe we would have found something else. But no one interprets their results in terms of Adam, which puts in a whole load of assumptions on this. So, this leads me back. This was the final quote. We can always end with Noam Chomsky. There's a notion of success which I think is novel in the history of science. It interprets success as approximating unanalyzed data. This is the problem, right? Scientific success is to say, why did this work, not that it works, right? And having probabilities, allowing you to formulate your beliefs, seeing how they work, allows you to do that. And that's exciting. So therefore, I think this is the coolest things in sliced bread. So, I made fun of this in my first talk. There's no fun about this at all. We can now actually work with this thing. We can put the hypothesis space, we worked on that a lot, right? Now we can start doing stuff here. And that's really, really cool. So, just in summary, all I've talked about, GPs, hopefully you now think they're quite useful, right? Quite cool. If you've got uncertainties, none of my talk today is tied to Gaussian processes. Anything that gives you uncertainties, just think about them in this way. It's just simple math to work with GPs. Degrees of beliefs are really useful, right? That's how I can start exploring things, right? The uncertainty allows us to design rich strategies for how to acquire data. Super, super important point. And we can, if we have this factorization, especially in the factorization where we also have computation, we can design very simple, nice acquisition functions. Probabilistic numerics, what I just tried to do was just think about compute as just data. It's just the result of something that you're trying to understand. So, if this is the case, we should treat this exactly the same way we treat any other data. And clearly, computation is absolutely not truth, but everyone in my community considers it truth. It's not. Run it on a different computer, run it on, it's a little bit warmer, it's going to make different errors. So, why do we want to do this? Think about efficiency. How can I compute less? Like you might just be wasting compute, right? You've already as good as that. Downstream tasks, and then finally, learning and understanding algorithms in the relationship to data. And there's a great book on the thing I talked about now, which is free. We're organizing, or I'm attending, the first conference in this field, which is happening in a month's time. On this website, there's some really, really good taught material with workshops and so forth. And this community is very small, but it's getting very exciting. Like, things are happening. And some of the things that are really cool, we always think about, if you add probabilities, if you become Bayesian about something, it's going to cost you. The cool thing with they're now showing, they have ODE solvers, which are quicker than non-probabilistic ODE solvers. Because you know, when you're solving ODEs, right, I can have a step size of a mile, and then stuff happens, right? So what do we do with the deterministic one? We put it at the minimal one I need to capture, right? If I got this stuff, I'll make that step size, or very small, or make that step size, so you can actually be quicker and have uncertainties. Really exciting. So, with that, I'm going to end, and thank you very much. Whew, that was quick. We cut a half an hour, so crammed as much as I could. Good. Shoot.
I was wondering, in all of your methods, you were talking about sampling from sampling in general.
Yeah.
We've all used pseudo-random numbers
Yeah.
for the sampling and other like numerical approximations. How do you think that affects the whole process? And especially like you do research in deep learning. Do you think it's possible that deep learning models can learn the pseudo-sampling method or like the prime generator that gives the randomness somehow?
Super interesting, right? So there's a great paper by a fellow who wrote lots of single author papers that no one cared about in the 80s, called Tony O'Hagan. And he's written a paper called Markov Chain Monte Carlo is fundamentally unsound. And the argument here is exactly the thing that you say. We don't have random numbers. If you don't have random numbers, true random numbers, MCMC is flawed, right? And there's a big thing in that book exactly about this, right? And we need to take that. Can neural networks learn the random numbers that we put in? Absolutely, right? And this is exactly what, you know, the amount of things that people spend on setting the random number in a neural network is absurd, right? It's absolutely absurd that we do a thing like this, but a lot of the results requires you to do that, right? So I think that's absolutely true. One of the authors of that book, Mike Osborne, is very, very strong against MCMC in any situation whatsoever because of exactly this case, right? I think it kind of works for a lot of things, but yeah, there's an underlying thing which is fundamentally wrong, right? It is the deterministic algorithm, right? There isn't stochasticity in it. Cool.
¿Alguna otra pregunta?
Okay, no more questions. If anyone, I'm gonna head straight to the airport now to head back, sadly. But if anyone has any questions or want to chat more about these kind of things, just feel free to contact me. I'm sure it's reasonably easy. I got a weird name, so if you search for me, you'll find my website and you can find my email. Very happy to talk about this. It's been a real pleasure chatting about things here. And I think the key thing is machine learning has a very annoying narrative, right? We're solving the world, it's like big and brash and all these things. Try to not be fooled by that, right? Try and actually go into the thing, and you as statisticians will see, is that what you're doing, right? It's just a lot of nonsense around it, and I think the real core work is coming from people who have a solid statistical background. Because eventually, this story that I said about Spearman, who effectively said that, you know, horrible things, right? White men are, awful, eugenics, awful, right? Effectively led to a Second World War, right? Their views on people were horrible. Machine learning is soon going to end up there, right? When we're putting these systems, without having a clue of what they do, into computation. And then it's proper statisticians who's gonna help address this thing. So try and don't feel scared or annoyed. It's just a lot of talk, right? Cool. Very good. Thank you very much.